All right, AP Chemistry. This is a review assignment for the AP exam for Unit 3, which deals with intermolecular forces. It also deals with some other subjects. And the idea of this video is this is saved as a Unit 3 assignment on the AP Classroom if you wish to go in there. But if you just wish to watch this video, what I will try to do is get through these questions quickly. If you want to think about a question, then pause the video, but I'm going to try to make this video as short as possible without a lot of long explanations, and but I'll try to make them thorough explanations, okay? So again, you can do this in AP Classroom. It's under Unit 3 assignment, or you can just watch this video, but try to think about the questions at least a little bit rather than just watch the answer, okay? So let's go with this first one. A 0.10 molar, remember molar means moles per liter. It's a measure of concentration of a solution. How many moles of the solute you have in per liter of the solution. Sodium sulfate is a better conductor of electricity than 0.1 molar solution of sodium chloride, NaCl. Which of the following best explains the observation? This is not untypical for an AP question. They're actually giving you the answer. They're just telling you, asking you to explain it. So they're not asking you which is a better conductor of electricity and then explaining it. They're actually telling you which one is. Now you got to think of the reason of why that is. Okay. So Na2SO4 is more soluble in water than NaCl. That's a possibility. Na2SO4 has a higher molar mass. Molar mass has nothing to do with it. To prepare a given solution of to prepare a given volume 0.1 molar solution, the mass of Na2, it has nothing to do with mass. More moles of ions are present in a given volume of 0.1. That could be it. Because what causes something to be an electrolyte to conduct electricity is it has to have charged particles, ions, like Na+, H+, Cl-, those charged ions. So it could be D, could be A. The degree of dissociation of Na2SO4 in solution is significantly greater. Again, that's kind of the same as A. The answer is it's really how many of these ions you have. So the more moles of ions, so the answer to this one would be D. It's D. Okay, move on. A certain crystalline substance that has a low melting point does not conduct electricity in solution when melted. This substance is likely to be. So just think of this example. When you heat salt and you heat sugar, they both look the same, but the sugar melts faster and it turns brown and turns black if you've ever done that. So sugar would melt faster and at a lower temperature than salt. Sugar is a covalent bond. For example, C6H12O6. Salt, NaCl, is an ionic bond. So if this crystalline substance does not conduct electricity, and that's typical of covalent bonds, they don't conduct electricity because they don't have loose charges floating around. So if it doesn't conduct electricity and it melts at a low temperature, it's likely to be covalent. Now, you see covalent network solid. That's actually a very strong bond. That would melt at a very high temperature. That would be a diamond. The answer is a molecular solid. That's another name for a covalent bond, is a molecular solid, because covalent bonds form molecules. So the answer to this one is E. A sample of a hard solid binary compound at room temperature did not conduct electricity as a pure solid, but became highly conductive when dissolved in water. Well, let me give you an example of that. Salt. Salt, just sitting in a salt shaker, cannot conduct electricity because it's electrically neutral. You have a positive and negative charge together. There's no way to transport electrons. But when you dissolve salt in water, you have Na+ and Cl-. You have ions, and that will conduct electricity. So what they're describing here is an ionic compound. So which of the following types of interactions is most likely found between the particles? And the answer is to that is A. And that's an ionic compound. Next up, gives you a structure, and then there's an unknown atom at the end of it where the X is. And it says the structure of haloacetic acids, those are acetic acids with a halogen at the end where that X is. So X is either fluorine, chlorine, bromine, or iodine. Those are the halogens, second to last column, is shown above. The dissociation constants, which is how much a molecule wants to dissolve, and molar masses of 4 haloacetic acids are listed down below. The question is which compound, chloroacetic or iodoacetic acid, most likely has a lower boiling point. So just remember, when it comes to intermolecular forces determine whether a substance is a solid, liquid, or gas. That's not a chemical change, that's a physical change. And that's determined by whether the molecules or the particles really want to stick together. So if it has a low boiling point, it means it doesn't take very much energy to break the molecules apart and make them float off into space. So that means they have weak intermolecular forces. So it's asking which of those has the weakest intermolecular forces, but it's only giving you the choice between chloroacetic acid and iodoacetic acid. The answer to that would be that chloroacetic acid has the London dispersion forces are weaker because it's a smaller molecule. When it comes to London dispersion forces, the bigger molecule wins. It has the strongest London dispersion forces because it has the most electrons. Remember that London dispersion forces are caused by electrons temporarily getting pushed to one side of the molecule and creating a temporary dipole. And since iodoacetic is bigger than chloroacetic, it will have the stronger London dispersion forces and therefore have the higher boiling point. It takes more energy to get those molecules to break apart. Let me just check that answer. And yes, the answer is A. Okay, so down here they actually give you an explanation. So chlorine atom has fewer occupied shells than iodine. Chloroacetic molecule thus has a smaller, less polarizable electron cloud. It's the idea, the more electrons, the more polarizable it is. The more electrons that can be pushed off to the side. Okay, so it has weaker London dispersion forces, and that gives it a lower boiling point. All right, we keep going. Okay, so what you see is you have a diatomic gas here. You have two identical atoms. It could be H2 atoms, it could be O2 atoms, something where they're the same and they're in a gas form. So the question is, the diagram above is a molecular model of gaseous diatomic element that is just above the boiling point. Intermolecular forces between the gas molecules will cause them to condense into a liquid phase if the temperature is lowered. Which of the following best describes how the model is limited in its depiction of the phenomena? So let's cover up the answer first and think about that. So it does not show how hydrogen bonds are constantly forming. No. Hydrogen bonds are the strongest type of intermolecular forces. They do not form in gases. So that would not be it. The temperature would they would have to be in liquid form at least, or solid form, to form hydrogen bonds. Those are the strongest intermolecular forces. Let's remind what they are. It's a hydrogen attached to either a nitrogen, oxygen, or fluorine, and that hydrogen attaches to the lone pair of the nitrogen, oxygen, or fluorine of a different molecule. So it can only be a nitrogen, oxygen, and fluorine atom that it's attaching to, and it's attaching to the lone pair. So that's not a chemical bond, it's just a strong intermolecular force. Okay, so B. It does not show the interactions between ions. There's no ions here. These are diatomic molecules. They're not charged ions. There's no ions there. It does not show the interacting permanent dipoles. You can see that when you have two of the same type of atom as you do here, there's no dipole. It's like two hydrogens are equally electronegative, so they don't pull the electrons to one side or the other. They're equally strong guys having a tug of war. So the electrons are going to be equally spread out. So permanent dipoles have nothing to do with it. 4. It does not show how the temporary fluctuating dipoles of the molecular electron cloud result in a net force. Yes, that's true. Nonpolar molecules only have one type of force between them. Those are London dispersion forces, and those are temporary dipoles where the electrons shift over to one side of the molecule. So the answer to that would be D. It does not show how the temporary fluctuating dipoles result in a net force and therefore may be causing them to attract. Okay? All right. So this is a free response question. For parts of the free response question that require calculation. Okay, answer the following questions. I'm down below the diagrams. Answer the following questions about CH4 and CCl4. Well, the first thing I can tell you is they are both symmetrical. They're nonpolar. They have 4 bonding domains and no lone pair electrons, no lone electron pairs. What that means is they're going to be nonpolar. For something to be polar, that is to pull the electrons to one side, it has to almost always has to have lone pair electrons. These don't have any. So these are both tetrahedral molecules because they bond on 4 sides with no lone pairs. It's just that the carbon tetrachloride is bigger, obviously, and has more electrons. So if they're both nonpolar, the only forces, intermolecular forces in nonpolar molecules is London dispersion. And the rule is the molecule with the most electrons in London dispersion forces wins. It has the greatest London dispersion forces because you can polarize it more. You can push more electrons off to the side and give it a stronger London dispersion force. So A, which compound has the higher boiling point? The answer is CCl4 because it has stronger London dispersion forces that will hold the molecules together tighter. Smaller molecule doesn't have strong London dispersion forces. B, at 400 K, both compounds are gases. At this temperature, which compound behaves more like an ideal gas? Okay, it would be CCH4. An ideal gas means that the gas molecules do not want to stick together or interfere with each other. So if they start sticking together, then they start becoming like a liquid. That's what a liquid is when molecules start to stick together. If they stick together really tightly, then they become a solid. But you want them to not stick together if they're going to be a ideal gas. That means you want the weakest possible London dispersion forces or intermolecular forces in general, and that would be CCH4. So CCH4 will behave more like an ideal gas because CCH4 molecules do not attract each other. C, CCl4 is placed in previously evacuated container at 30 C, and some of the CCl4 evaporates. In the box below, draw a particulate diagram that show the species in the container after some CCl4 evaporated. The phase of the species should be indicated by spacing. First of all, CCl4 is a covalent bond, so it forms molecules. They do not break apart. Okay, molecules don't break apart. This is not an ionic compound like NaCl where they come apart into ions. So the CCl4 is not going to come apart even at high temperature. What will simply happen is the CCl4 molecules will separate. So what you would draw is, let me see if they actually have the diagram. You just draw some of them up above and some of them down below. Let me see, they do show an answer for this, I'm pretty sure, and a diagram, rather than talk you through a diagram. Oh, shoot. Part C. Well, they don't draw the diagram, so let me describe what it would look like. It would look like the CCl4. Forget about the Cl2, Cl, or C. You're not going to see any of those. All you're going to see is CCl4. And the ones down at the bottom will be close together because they're forming a liquid. They're sticking together. And then you'd have some of them up above separated, which would be a gas. So those are separate molecules floating around. So down at the bottom, they're sticking together like a liquid. Up above, they're a gas, and they're separated. Okay, move on. Okay, 4 different liquid compounds in flask at 20 degrees centigrade represented above. The table below identifies the compounds. Flask C shows the most particles in vapor phase, as you can see. Which of the following is not shown in the model, but best helps explain why flask C contains pentane, which is the smallest? Well, again, it's the smallest molecule These are all hydrocarbons. The only intermolecular forces they have are London dispersion forces. Those are those temporary dipoles when the electrons get pushed over to one side of the molecule. So the smallest molecule is going to have the weakest London dispersion forces and therefore the lowest boiling point. Boiling point is how much energy it takes to get those molecules to fly off into the sky. Okay, so since pentane has the lowest boiling point, it has the weakest London dispersion forces, and that stands to reason because it's the smallest molecule. Okay, so this is multiple choice. Whoop, there's the answer. So the strength of intermolecular forces between the particles in the liquid. So that's what we just said. Okay, you take the answers down so you have a chance to think before we go into the answers. Okay, next. Refer to the three identical rigid containers. So that means the volume's constant under conditions given below. So methane, ethane, butane. If the pressure of each gas is increased at a constant temperature until condensation occurs, which gas will condense at the lowest pressure? Okay, so again, the bigger molecule, these are all hydrocarbons. The only forces are London dispersion forces. The bigger the molecule, the stronger the London dispersion forces. So that means the bigger of these molecules will have strongest London dispersion forces. So at a given temperature and pressure, butane, which is the biggest, will tend to want to get together. It'll tend to want to stick to other butane molecules because it has higher London dispersion forces between the molecules to cause them to stick together. So the one that will happen at the lowest pressure, in other words, you don't have to push it together to stick together with other, it would be the butane. Methane would have to be at a very high pressure, the smallest of those, to want to stick to other methane molecules. Methane is always a gas. Okay, so the answer is, there it is, butane. Okay, move on. All right, in solid methane, the forces between neighboring CH4 molecules are best characterized as E, London dispersion forces. That's all it has. They don't have ion dipole. There's all the types of bonds that you have. Ion dipole, hydrogen bonds. It doesn't say dipole, but covalent bonds. Covalent or ionic bonds are chemical bonds. They form actual compounds. That's the difference between H2 plus O2 equals H2O. It gives you a totally new substance. Ionic and covalent bonds. Hydrogen bonds, ion dipole, and London are intermolecular forces. They simply take a particular compound and determine what its state of matter is, whether it's a solid, liquid, or a gas. So intermolecular forces determine whether solid, liquid, or gas. Chemical bonds, such as metallic, covalent, ionic, determine new chemical structures, new chemical compounds. Okay, so oh, there it is, London dispersion. Okay, next. Okay, which of the following liquids do the intermolecular forces include ion dipole forces? Well, F2 is nonpolar. It's two equally strong guys having a tug of war, so there's no polarity there. It's nonpolar. CH4 is two different elements, but it's nonpolar. It's four hydrogens attached to a carbon. That forms a tetrahedral structure. It's an AX4E3, meaning it's perfectly symmetrical, no non-bonding electrons, no lone pairs, and so it's going to be nonpolar. CF4, same thing. It's nonpolar. It's just a bigger atom on the outside, but it's symmetrical and it doesn't have polarity. The one that's going to have polarity is the CH2F2, and F is fluorine is the most electronegative element, so it's going to definitely have dipole-dipole forces. So the answer to that one is D. Okay, in which of the following processes are covalent bonds broken? All right. So, I2 solid, I2 gas. No, that's a change of state from a solid to a gas. That's a function of intermolecular forces. CO2 solid, CO2 gas, same thing. Intermolecular forces determine whether CO2 is a solid or a gas. It's still CO2. It's still the same chemical substance. It's just whether it's in solid form, like graphite, or floating around in the air, like carbon dioxide that we breathe. NaCl solid, NaCl liquid. Again, that's the difference in state. That's an intermolecular force. Carbon, diamond to carbon, graphite. Yes, diamond forms what's called a covalent network solid. It's a three-dimensional bunch of carbon, just pure carbon atoms in three-dimensional structure. And when it breaks down into carbon gas, that means the covalent bonds are broken. And then Fe solid, Fe liquid, again, that's intermolecular forces. So the answer to that one is D. Going from diamond to carbon gas is a breakdown of the covalent bonds between the carbon atoms. Okay, is a strong electrolyte... Okay, it seems like an incomplete question. Is a strong electrolyte an aqueous solution? Well, which is a strong electrolyte? NH3 ammonia is covalently bonded. Covalent bonds don't form very strong electrolytes at all. BH3 is also covalently bonded. Again, non-metal or covalent bonds. H2, absolutely not. Covalently bond, it's non-polar. It's not an electrolyte. Electrolyte means conducts electricity. H2S, same thing. The one that would be is HBr. That's hydrobromic acid. It will dissolve to form hydrogen ions and bromine ions in solution. So you have a bunch of plus charges and a bunch of negative charges, minus charges for the bromine floating around. And so that would be an electrolyte. So the answer to that one is E. Okay, which of the substances listed above has the highest boiling point and why? So again, highest boiling point means it takes the most energy to break the molecules apart. So that means you're looking for the one with the strongest intermolecular forces. That one would have the highest boiling point because it would take more energy to break those intermolecular forces. So CH4 is not strong at all. Small. Neon is a noble gas. It's already boiled. Neon will almost never be as a liquid or a solid. It's just atoms. They're not polar. You can't have a polar atom. And so they're already floating as a gas. C2H6 is nonpolar. HF. Now, HF is polar. It's hydrofluoric acid. Because fluorine is the most electronegative element, it will be polar. So since you have a polar molecule, it will stick to other polar molecules. Polar, dipole means it has a dipole, positive end and negative end, are always going to be stronger bonds than, almost always, I can't say always, almost always than London dispersion forces, and therefore it would be HF. And there it is. Okay, and I forgot to mention, it forms hydrogen bonds. The hydrogen on the fluorine can be attracted to another fluorine or another oxygen or another nitrogen. Nitrogen, oxygen, fluorine for hydrogen bonds. So yes, that's another explanation. Okay. All right, keep going. Okay, on the basis of strength of intermolecular forces, which of the following elements would be expected to have the highest melting point? So again, highest melting point means it's going to break the bonds between the molecules. It means you need the most energy, so it again means strongest intermolecular forces. So which one? N2Kr, F2, Cl2, Br2. The answer to that is you look for the one that's the biggest, and the biggest would be Br2. That, if you look on your periodic table, it's the biggest of those molecules, and therefore it can have the strongest London dispersion forces. All of those molecules, well, krypton is an atom, but all of the molecules are nonpolar. So the only forces they have are London dispersion, and the biggest molecule wins with London dispersion forces. It has the strongest, so that's going to be Br2. Okay, there you go. Let's keep going. Okay, so you're given a couple of compounds here. Ethylene is the first one, propanol is the second one, or ethane is the first one, propanol is the second one. So ethane is totally nonpolar. It's perfectly symmetrical. It's a hydrocarbon. Hydrocarbons are nonpolar. The propanol is polar. It has an oxygen, which is highly electronegative, sitting way down at one end. So it's going to be pulling all the electrons in the entire molecule down to that end. So that means that propanol can have dipole intermolecular forces. It can also have hydrogen bonds because you have a hydrogen attached to an oxygen. Hydrogen attached to nitrogen, oxygen, or fluorine can form hydrogen bonds with the lone pair of another nitrogen, oxygen, or fluorine. So the top one, the ethane, can only have London dispersion, very weak forces. The bottom one can have all kinds of forces, everything, including hydrogen bonds. So based on the structural formulas, which of the following identifies a compound that is more soluble in water and helps to explain why? Well, water can form hydrogen bonds, and the propanol can form hydrogen bonds. So the propanol has more ways to bond. Remember, water is a polar molecule. Propanol is a polar molecule. So its propanol is going to want to dissolve in water. It's going to want to break apart and attach to water molecules. Ethane's nonpolar. Nonpolar doesn't want to attach to polar molecules, so you'll have very little with the ethane. So the answer would be, and which explains why, is all the different types of bonds. So the answer to this one is D, propanol, because its molecules can form hydrogen bonds with water molecules, but those of ethane cannot. That is the correct answer. Okay, move on. All right. Again, we're focusing on intermolecular forces, so be sure you understand. Let me repeat. Intermolecular forces will take two molecules that have a certain chemical structure and break them apart, determine whether they stick together really hard, really well, like a solid, or kind of stick together but can move around each other like a liquid, or don't stick together at all like a gas. That's what intermolecular forces determine. And those are London dispersion forces, dipole-dipole interactions like between water, and hydrogen bonds like between water or between anything that has a hydrogen attached to a nitrogen, a hydrogen attached to an oxygen, a hydrogen attached to a fluorine. Hydrogen bonds are very specific. They have to have those particular combinations. Okay, boiling points of the elements helium, neon, argon, krypton, these are all noble gases, increase in that order. Which of the following statements accounts for the increase? Well, they're all noble gases. The only kind of forces they have are London dispersion. And so yes, as you get a bigger and bigger atom or molecule, but in this case atom, you get stronger London dispersion forces because you have more electrons that can get pushed over to one side and create that temporary dipole. So the answer to that is A. And there it is. Okay, 17. The diagram above shows the molecule Br2 and I2 drawn on the same scale. So you can see these are both nonpolar because it's two identical elements, and iodine is bigger, which means it's going to have stronger London dispersion forces. So we can draw those conclusions right now. Which of the following is the best explanation for the difference in boiling points, which are, okay, so iodine's going to have a higher boiling point. It has more electrons. It can form stronger London dispersion forces to attach one iodine molecule to another iodine molecule. And so iodine's going to stick together better, stronger London dispersion. That means it's going to take more energy to break iodine molecules apart and get them to float off into space. So that means it's asking which is the best explanation. So let's look at the explanations. Solid iodine is a network covalent. No, it's not. Covalent bonds in iodine molecules are weaker. That's not true. And it has nothing to do with it. It has nothing to do with the bonds, the covalent bonds. It has to do with intermolecular forces. I2 molecules have electron cloud that is more polarizable than Br2. That is correct. Bromine has greater electronegativity. That has nothing to do with it. So it's C. I2 molecules have electron clouds that are more polarizable because it has more electrons than those of Br2 molecules. Thus, London dispersion forces are stronger in liquid I2. That's correct. So C is the answer on that. Okay, let's move on to the next one. We're on number 18. We're halfway through. We have about 35 questions here. Okay, you should be familiar with this diagram. What it is saying is that for a substance, it's in solid form where you see P. Now for water, this would be below 0 degrees centigrade. It's solid. Then when you get it up, let me describe water to you and then let's talk about this. When you get it up to 0 degrees centigrade, it's ice. It's ice when it's below 0. Then when you get it up to 0, the ice starts to melt. While the ice is melting, the temperature stays the same. Remember that. While ice is in the process of going from all ice to all liquid water, the temperature stays the same, 0 degrees. Then as you keep adding heat, the temperature goes up and up and up from 0 to 100. That would be R on this diagram. Then when you get to 100 degrees, which would be S on this diagram, while the water is boiling, it starts to boil at 100, it stays at 100 degrees. The liquid water doesn't go above 100 degrees because any molecules that are above 100 degrees will float away as a gas, as vapor, as steam. So as long as there's water boiling, the temperature in the water stays at 100. And then once you get up above the boiling point where everything is gas, and then you move the thermometer into the gas can increase its temperature above 100 degrees. So you have these 5 different locations. The 2 flat lines, the first one where Q is where the ice is turning into water, and the second one where S is where the water is turning into steam. And then the others are where P is all ice, but the temperature is going up. Where R is all water, but the temperature is going up. And where T is all steam, but the temperature is going up. Okay, so this is not talking about water. This is talking about CH4. So it has a very, very low freezing point. You notice the temperature on the Kelvin scale is only 60 above Kelvin. That's really, really, really cold. This is not centigrade. This is Kelvin. So it takes a really cold temperature to get methane to form a solid. Okay, so let's read this. Let's read the question. The enthalpy of vaporization, that's how much heat it takes to make this substance boil. That's what you would need at S. So you see S down below says delta H vape. That's how many kilojoules per mole of methane you have to turn liquid methane into gaseous methane. You need 8.2 kilojoules per mole, and that's called the heat of vaporization, or the delta H of vaporization, or the heat of vaporization. The heat that it takes to cause something to melt from solid to liquid, you'll see that at point Q, is the heat of fusion. It's called the heat of fusion. Okay, but they're asking about the heat of vaporization. So the enthalpy of vaporization for water is 40.7 kilojoules per mole. Which of the following best explains why the enthalpy of vaporization of methane is less than water? Well, it just simply has weaker intermolecular forces. That's the deal. Water has hydrogen bonds, dipole-dipole interactions, as well as London dispersion forces, which are not very important in water. Whereas methane only has London dispersion and therefore very weak intermolecular forces. So the answer to this one would be B. Methane has weaker dispersion forces. Density has nothing to do with it. No, it could be A. Methane, yeah, I would say this one. Methane, actually, water actually does have stronger dispersion forces than methane, but that's not the point. The point is methane does not exhibit hydrogen bonding, but water does. So let's just check that answer. But that's pretty sure that's the right answer. That is, A is right. So it's because water can do hydrogen bonding and methane can't. Okay, let's keep rolling here. Okay, and let's look at the same question. I think I didn't click. Okay, there we go. All right, here we go. Question 20. So you see some different structures, mostly carbon-hydrogen. Let's look at them for a second. Okay, so butane is going to have the weakest intermolecular forces because it's a pure hydrocarbon, purely symmetrical, only has London dispersion. The acetone, the one at the top, has an oxygen thrown in there. That means it's going to be polar. Because oxygen is highly electronegative, it's going to tend to want to pull the electrons in the whole molecule kind of towards it. Not all the way towards it, but kind of pull them in its direction. So that has dipole-dipole. Propanol can have hydrogen bonds because it's a hydrogen attached to an oxygen. So that hydrogen can go find the lone pair on another either oxygen, fluorine, or nitrogen atom in another molecule, and that's the strongest type of bond is London dispersion. So I'm just drawing some conclusion before I even look at the question. So let's read the question. The table above shows the structural formulas molar mass for 3 compounds. Which of the following lists compounds in order of boiling points? So stronger London dispersion forces means higher boiling point. It means it's going to take more energy to break those molecules apart, and that's what boiling point is. So the highest is going to be propanol, the lowest is going to be butane. So let's find that one. So it would be B. Butane, it said, be sure you get it right, increasing boiling points. Yeah, so butane is the lowest boiling point, acetone is in the middle, and propanol is the highest. Okay, we'll just check that, and that's the answer. Okay. All right. So you have solid magnesium oxide and liquid magnesium oxide. So basically you've taken the magnesium oxide and thrown it into water. So the ions break apart. You have Mg2+ and you have O2-. ions floating around there inside the box. Whereas when it's solid MgO, everything's electrically neutral. Your pluses and minuses balance out, and so it's electrically neutral. That means solid MgO will not conduct electricity. You need ions, you need charged particles to attract and repel electrons in order for electricity to flow. So electricity will flow through liquid MgO because they have a bunch of positive and negative charges there, but not through solid because the entire structure is electrically neutral. So based on the diagram above, which of the following best helps to explain why MgO is not able to conduct electricity, but liquid MgO, solid MgO is not, but liquid MgO is. Okay, so MgO does not contain free electron, MgO solid does not contain, but MgO liquid contains free electrons. That might be the right answer. MgO solid contains no water. That has nothing to do with it. MgO solid consists of separate Mg. Yes, that's actually it. The MgO will attract electrons, but it's not that it has separate electrons or free electrons. So MgO consists of separating Mg2 plus MgO, but MgO contains MgO molecules that Oh, I read the wrong answer. So it is the bottom. So it is the right explanation, MgO2 plus MgO2 minus. But let's see what the difference is. But MgO at liquid contains MgO molecules. That's not true. MgO is an ionic compound. They're called formula units. Molecules don't break apart in water. They don't dissolve in water. So that's where I didn't read the question carefully, the answer carefully. Okay, MgO solid consists of separate, but MgO liquid, the ions are free to move and conduct electricity. So yeah, it's D. Okay. So they have to be an ionized form in order to conduct electricity. That's why sugar water, that's why covalent bonds don't conduct electricity. And ionic solids don't conduct electricity because they're electrically neutral. You have to dissolve them and break them into ions. Okay, let's keep going. So, liquefied hydrogen halides, these are all acids, hydrofluoric, hydrochloric, hydrobromic, hydroiodic, have normal boiling points given above. Okay. The relatively high boiling point of HF can be correctly explained by which of the following? Well, they're all polar, so they all have dipole-dipole. But what hydrogen fluoride has that the other three don't is the ability to make hydrogen bonds. Only fluorine, oxygen, and nitrogen can form hydrogen bonds, and those are the strongest intermolecular forces. So the answer is E. Hydrofluoric molecules tend to form hydrogen bonds. Okay, so you're given carbon sulfide and carbon tetrachloride. Let's see, boiling point of carbon sulfide is lower. That means it has weaker intermolecular forces. It's smaller, so it has a lower mass. That would also indicate that its London dispersion forces are weaker because it has fewer electrons. So based on the information in the table above, which liquid has the higher equilibrium vapor pressure at 25 degrees? Okay, so we didn't really talk much about vapor pressure. In fact, I don't think we talked about it in this class at all. It's a very simple concept. If you've got a glass of water, up above that water, there's going to be some water molecules that are broken away and kind of temporarily evaporated just above the surface of the water. And then maybe they'll fall back into the water. But there's always a few water molecules of vapor right above the water, and that's called vapor pressure. That's all it is. It's just the vapor of the water that's up above the liquid water. In this case, it's vapor of these two substances. So what are they asking? Which has the higher equilibrium vapor pressure? It's the one that will have the most molecules up above the surface of the liquid. That'll have a higher vapor pressure. That kind of makes sense. Okay, and which one would that be? It would be the one with the weakest intermolecular forces, because it means it's easier for those molecules to break away from the liquid and float up above the surface of the liquid. So let me say that again. If the molecules have weak intermolecular attractions to each other, they'll more easily break away from the liquid and float up above the liquid. And that means it has a higher vapor pressure. So the one that will have they're asking for the one with a higher vapor pressure is going to be CS2. because it has a small molar mass and we'll forget the molar mass, because it has a lower boiling point, it means more of its molecules will be floating up above the CS2 liquid, and therefore it will have a weaker intermolecular forces. So CS2 liquid because it has stronger London dispersion. No. B, CS2 because it has weaker London dispersion forces. That's the answer. Okay. All right, next. Okay, so now you have, where'd I go? I think I skipped one. Okay. Let's see here. Let's close this. So now you have two compounds, and you have COH and CCl. Okay, so structural formula of those two compounds. For each compound, identify all types of intermolecular forces present in the liquid. Okay, so glycerol has all three types of intermolecular forces. Everything has London dispersion forces. It's just sometimes they're not the most important, and so you don't even think about them. It also is polar because it's a lopsided molecule. It has oxygens over on one side, so it has dipole-dipole. And because it has an H connected to an O, it can also form hydrogen bonds. The CCl has London dispersion. It also is polar because the Cl is electronegative, and more electronegative than hydrogen. It pulls the electrons towards it. But you can't form hydrogen bonds with chlorine. And so those are the two. So glycerol has three: London dispersion, dipole-dipole, hydrogen bonds, and trichloropropane has two: London dispersion and dipole-dipole. Okay, so B. So let me just go ahead and talk you through this one. So to figure out how much heat it would take to heat up 500 grams of water 80 degrees, you use the formula Q. It's on your formula sheet. Q, that's heat, equals mass, M, specific heat of water, C, delta T, change in temperature. So you have the mass of the water, you have the specific heat, 4.184, and you have the change in temperature, 80 degrees. And if you calculate that, you get 167.4 kilojoules. 167.4 kilojoules are required to heat that much water by 80 degrees. Now it tells you that the entropy is that the glycerol is going to put out 1,654 kilojoules per mole. So you need roughly, if you need 167 kilojoules to heat up the water, and the glycerol puts out 1,654, I'm using rough numbers here, it takes about 1/10 of a mole of glycerol, 1/10 of 1654 to equal 167. So it takes 1/10 of a mole of glycerol. If the molar mass of glycerol is 92.9 and you need 1/10 of a mole, then you have 1/10 of that number of grams, which is 1/10 of 92.9. That would be about 9 or 10. So about 9 or 10 grams of glycerol. If you want to see that worked on writing, I hate to talk you through numbers, but I don't have a way to show it on the screen, come to one of the meetings and we can go over that problem, okay? All right, let's keep going. Actually, they may show you the calculation down here in the answers. Let's see. Are they going to show you the answer? Part A. Yeah, it talks about the types of forces there. For the second one, Part B. Here, they'll show you the calculation here. Oh, it's messy. You can see it. It's what I was telling you. Anyway, it's Q equals MC delta T. You figure out the heat that's required using MC delta T. They give you all three of those variables. You can see them there. And then they'll figure out the heat required to heat up that much water. And then you figure out how many moles of glycerol does it take, because they give you the one. Anyway, there's the answer if you want to write that down. You'll see they came up with the answer I came up with. About 9 or 10 grams of glycerol are required. And I'm going to leave it at that. They're not going to ask you heavy numbers questions on this AP. There just isn't time for it for you to do calculations like that. Okay, let's keep rolling here. We're doing pretty good as far as time. All right, London dispersion forces are weakest in which of the following gases? So H2O2 Ce. So they're going to be weakest in the one that has the least electrons, and that's going to be H2. There it is, okay? Again, just count electrons. The ones with the most electrons has the highest London dispersion forces. That only applies to London dispersion, not to hydrogen bonds or dipole-dipole. Okay, keep moving. All right, molecular formula, C2H6, C4H10, the mass. Those are both nonpolar molecules. They're hydrocarbons. The one with the greater mass means the greater number of electrons. That means butane's going to have, they're only going to have London dispersion forces, and butane is going to have the stronger London dispersion forces because it's the bigger molecule and has the most electrons. So now let's read the question. The molecular formula, molar mass of two straight chain hydrocarbons are listed above based on the information. Which compound has the higher boiling point? Butane does. Okay, that's just that simple. It has more electrons, stronger London dispersion forces. So the answer is B, C4H10, because it has more electrons, resulting in greater polarizability. Kind of learn words like that, polarizability, and stronger dispersion forces. Okay, so that's the answer. Let's move on. Okay, let's see this one. Some building materials contain small capsules filled with paraffin wax. Okay, that's the kind of wax that's used in candles to improve the insulating properties of the material. The melting and freezing points of paraffin inside the capsules in the material helps to regulate temperature. Paraffin wax begins to melt at 37 degrees centigrade. So that's about 100 degrees Fahrenheit. It's kind of a warm day. So that you see candle wax kind of melts when it gets really hot in the room. While the wax is melting, is the net flow of thermal energy from the wax to the surroundings or from the surroundings to the wax? Well, if something is melting, that means the molecules are breaking apart. It takes energy to break molecules apart. That means the energy has to be going into the paraffin wax. Just like when ice melts, the energy has to be going into the ice to break apart the water molecules so that they separate. Okay, so that's the answer to that. B, calculate the amount of thermal energy in kilojoules. I don't know if I want to do this. Again, numbers are just not going to be on the test. That is required to melt 15.2 grams of solid paraffin wax when the temperature of the surrounding is above the melting point of paraffin. The molar mass of paraffin, they give you that, and the molar heat of fusion. Okay, so what you're trying to do is you're trying to get the amount of kilojoules, and they give you two numbers there. Let's just approach this conceptually. You have the molar mass. You have the molar mass of paraffin at grams per mole, and they tell you how many grams. So using the grams of paraffin and the molar mass, you figure out how many moles of paraffin. Okay. Then with the number of moles of paraffin, you multiply that by kilojoules per mole, 48.78, and moles will cancel out, and you end up with kilojoules. So just kind of play around with the units of measure until you get them to give you what you want. You want kilojoules. So how do you get kilojoules out of those three numbers? 15.2 grams, 282 grams per mole, 48.78 kilojoules per mole. Just line them up until they cancel out to where you get kilojoules, and that would be your answer. When paraffin wax melts, its density decreases. Provide the particulate level explanation. So you would just draw little circles. They don't expect you to know paraffin's a big molecule. So just draw little circles that say paraffin. Or something like that. And just show how some of them on the interior, just think of a candle, the interior wax is still sticking together, it's solid, but the ones on the outside are starting to separate. So you show the little circle with paraffin written in it, separating out around the sides, but in the interior they're stuck together pretty solidly. Okay, let's see if they show this one. They tend to not show diagrams in these. Okay, let's get our answers. A. That the melting is endothermic. Yeah, I should have used that word, and you should use it. It's endothermic. The heat goes into it, so in order for it to melt. So use the word endothermic. That was wrong of me to not do that. Okay, there's the calculation I just showed you. You got 15.2 grams. You got to convert to moles, so use molar mass conversion, and then you get the moles to cancel out, and multiplying by kilojoules over moles, and you get the number of kilojoules that would be required. It's a pretty simple calculation. See if they give you a diagram for C. No, they don't. I don't know. Anyway, I think my description was about as good as you're going to get there. Okay, let's keep going. Okie doke. Thymine, adenine form a... By the way, when you get all this stuff, thymine, adenine, don't let it throw you. Forget about all that mumbo-jumbo. Just focus on the diagrams or on the key facts. You don't need to even know what thiamine and adenine are. I think most of you know from biology, but anyway, let's just cut to the chase here. The bases are attached to the, it says, which of the following diagrams shows the correct representation of the hydrogen bonding? Can you recognize a hydrogen bond? Okay, well, A, no. The hydrogens, you see two hydrogens with the dashed lines, and yes, those hydrogens are trying to hydrogen bond with a nitrogen and an oxygen, which is permitted, but that hydrogen in its own molecule has to be attached to a hydrogen, to a nitrogen, oxygen, or fluorine, H, O, or F. It's not. In both of those, where the dashed lines are, those hydrogens are attached to carbon. So you cannot hydrogen bond when the hydrogen's attached to carbon. It must be attached to nitrogen, oxygen, fluorine, and it must be hydrogen bonding with a lone pair on nitrogen, oxygen, and fluorine. Anything other than those three elements, you can't have a hydrogen bond. The next one, let's go down. Same thing. You got the, let's see, you got the hydrogen attached to the carbon in B, so that's no good. Next one down. Same thing. You got the hydrogen attached to carbons. No good. Next one down. This one's the right answer. You've got the hydrogen attached to a nitrogen and then forming a hydrogen bond with an oxygen in one case. In the other case, you have the hydrogen attached to a nitrogen and hydrogen bonding with a nitrogen. That's legal. It can mix and match any of those combinations. Nitrogen, oxygen, fluorine with nitrogen, oxygen, fluorine with a hydrogen in between them. Okay? So there's your answer. All right, next up. Okay, so right away we see nonane and trifluoropentane. Nonane is a bigger, they're both nonpolar. I take that back. Okay, so they're not both nonpolar. The trifluoropentane has got fluorines, which are highly electronegative. They're going to pull the electrons over to it. So the nonane is nonpolar. The tripentylfluorine is polar. So let's see, which one has the higher boiling point? It's going to be, now you would guess it's going to be the one that's polar. But this is one that fooled me. The answer is carbon chains are longer in nonane than they are in the tripentafluorine. So they're saying that that one's going to have the higher boiling point. I got this one wrong. I thought since the trifluoropentane has highly polar atoms in fluorine, it was going to be dipole-dipole and be stronger. It turns out it's not. And here's the moral of the story. If you have a big enough nonpolar molecule, a really big hydrocarbon, like nonane, it can actually have stronger London dispersion forces attractions, because that's all nonane can have, it's nonpolar, than something that's polar. Okay? So that one tricked me, and well, it shouldn't have tricked me if I'd read the chart here, because it's telling you nonane has a higher boiling point. But so you have to justify it. So the only way you could justify it is that it has to have stronger London dispersion forces, because that's all it has. You just have to go to the only answer that's possible. Okay. All right. I'm going to do one more, and then I'm going to end this. That'll be 30 questions that we've done. Some of them had multiple parts, so I think that's enough chemistry for one day. We'll be coming up on an hour, and I think I'm going to try to limit it to an hour each day. I don't want to burn you out or have you not do these because they seem like they're too long. Okay, let's do one more. This one's actually multiple choice. Draw a complete Lewis structure electron diagram for ethene in the appropriate cell below. I'm going to skip that one. I want to get to one more that's quick. Okay, use the principles of atomic structure and chemical bonding to explain the following. The atomic radius of lithium is larger than beryllium. Okay, lithium has, we've done this in one of the earlier videos that I did. Lithium has fewer protons to pull in on its second orbital electron. Therefore, the electron sits farther away. Beryllium has one more proton than lithium, so it pulls in harder on its two valence orbital electrons. So even though beryllium has more protons, neutrons, and electrons than lithium, it's smaller because the Z number, the Z effective of beryllium is greater than it is of lithium, and it pulls those valence electrons in tighter. Again, I've given this explanation on another video. The second ionization energy of potassium is greater than that of calcium. That's true, because calcium has two valence electrons. It can easily ionize both of those because it wants to become like the nearest noble gas, argon. So the second ionization energy for calcium is a third orbital electron. It will easily give up that second electron. Calcium will easily give up 2 electrons to be like argon. Potassium only has 1 valence electron, so it will only easily give up 1 electron. Once it gives that up, it will have the electron configuration of argon, and therefore it will its second ionization will be almost impossible. It'll be like argon. It'll be like a noble gas. So calcium easily gives up 2. Potassium only easily gives up 1. Carbon-to-carbon bond in C2H4 is greater. If you do the Lewis dot of C2H4, it's a double bond between the carbons, whereas C2H6 is only a single bond, so it has a stronger bond energy, and double bonds, remember, are also shorter. They have a shorter bond length and stronger energy. And D, the boiling point Cl2 is lower than the boiling point of Br2. Both of them are nonpolar. Br2 is larger, so it has more electrons. It only has London dispersion. Both of them only have London dispersion forces. The one with the most electrons wins, has the strongest London dispersion forces, and that would be bromine. Okay, I'm going to stop this now and put this up. Watch these. Try to pause a little bit and think about them before I give you the answer. I'm just moving right through and giving you the answers quickly. And that's it. I'll see you on another video tomorrow. Today is Friday, May the 8th. So try to do as many of these as you can. 3 hours a day if you can, okay? Alrighty, have a good day.